All right, welcome everyone. Today, we're diving into something that's absolutely critical for any site engineer, electrical load design. We're going to skip past the heavy textbook stuff and focus on what you actually need to know and do on the ground to get a project done safely, reliably, and up to code. Let's jump right in.
So, here's the big question, right? Because let's be real, when an electrical system fails, it's not just a headache, it's a huge safety risk. It can cause massive project delays, and it can cost a fortune. Getting this right from the very beginning isn't just important, it's non-negotiable. So, let's break down exactly how to do it.
Okay, so first things first. Everything, and I mean everything, starts right here. Before you even think about picking a cable or a breaker, you have to know exactly what you're up against. You've got to know the total demand the system is going to face. This calculation is the bedrock of your entire design.
Now, a classic rookie mistake is just adding up the wattage of every single piece of equipment. If you do that, you're going to end up with a system that's massively oversized, inefficient, and way too expensive. So instead, we use something called a demand factor. This helps us estimate the realistic peak load, the most power you'll likely draw at any one time, not the crazy number you'd get if every single thing was turned on at once.
So this is where it gets really interesting, because it shows you how we think about the real world. Lighting, we give that a factor of 1. Why? Because it's totally plausible that all the lights could be on at the same time. But sockets? We only figure about 80%. Because what are the chances that every single outlet is being used at the exact same moment? Pretty slim. And then you've got motors, jumping up to 1.25. So why the extra juice? Well, think about that initial kick they need to get going, that in-rush current. We have to account for that. This isn't just guesswork, it's smart engineering.
All right, Section 2, sizing our cables. We know how much power we need, so now we've got to figure out how to get it there safely. This is where we pick the arteries of our electrical system.
So picking a cable, it's not as simple as just looking up a chart and matching the current rating or the ampacity to your load. The real-world conditions on your site can dramatically change how much current a cable can safely handle. That's where derating factors come in, and I can't stress this enough. These are our mandatory reality check.
So here's the deal. You absolutely have to know your site's environment. I mean, think about a project in the Gulf, where it's regularly over 40 degrees Celsius. That same cable can't handle the same amount of current as it would somewhere cooler. That's your temperature factor. And what if you're bundling a bunch of cables together in a tray? They all generate heat, right? Well, they kind of cook each other, which reduces how much power each one can carry. That's the grouping factor. These aren't just suggestions. They're safety-critical calculations from standards like IEC 60502.
Okay, so we've got our load, we've got our cables. Now for what is arguably the most important step, making sure this whole system is safe, reliable, and fail-safe.
I want you to think about voltage just like water pressure in a pipe. The longer the pipe, or in our case the cable, the more pressure you lose by the time it gets to the end. That's voltage drop. If that drop is too big, your equipment is going to struggle. It might underperform, overheat, or just flat out get damaged. This is why we absolutely have to calculate it, especially for long cable runs.
So the industry has really strict limits on this, and for good reason. You'll see lighting circuits are held to a tighter standard. Only a 3% drop is allowed. That's because even a tiny drop in voltage can make lights flicker, and nobody wants that. Power circuits that run things like motors can handle a little more, up to 5%. If your calculation goes over these numbers, it means your cable is too small for that distance. Plain and simple.
Okay, next up, sizing the breaker. For any load that's going to be running for a while, say 3 hours or more, we need to build in a safety buffer. The rule of thumb is to pick a breaker that's rated for at least 125% of your load. This isn't random. It stops the breaker from tripping just because it gets a little warm during normal operation, but it will trip instantly when there's a real problem. Listen, if you walk away with only one thing today, please let it be this. This is the absolute golden rule of electrical safety. The breaker is the bodyguard for the cable. Its only job is to trip before the cable gets overloaded, overheats, and starts a fire. So the breaker's rating must be less than or equal to what the cable can handle. Every single time. No exceptions.
Okay, enough with the theory, right? Let's get our hands dirty and put all of this into practice. We're going to walk through a real-world example, something you'd see on a typical small commercial job, and design the system from the ground up.
And we're going to follow the exact same process you would on site. It's a simple, logical 3-step plan. First, we'll mill down the total load. Then, we pick the heart of the system, the main distribution board, or MDB. And finally, we'll get into the nitty-gritty of sizing each individual circuit cable and breaker.
Okay, step 1, the load calculation. So let's imagine for our building, we add everything up, lights, outlets, the HVAC system, and it comes to 27 kilowatts. That works out to about 46 amps. But, and this is key, we know everything isn't going to be on full blast at the same time. So we apply that diversity factor, bringing our final design current down to a much more realistic 32 amps.
So, with that 32 amp number in mind, we can pick our MDB. We go with a 63 amp main breaker. It's the next standard size up, which gives us our safety margin and a little room to grow. The bus bar inside is rated for 100 amps, again, thinking about future needs. That IP41 rating just means it's good for indoors, safe from tools, and a bit of dripping water. And that 25 kiloamp rating, that's its muscle. It tells us it can handle a massive short circuit without exploding.
And now we size each circuit that feeds out from that MDB. You can see how it all connects here, right? The big HVAC unit pulling 33 amps, it gets a beefy 10 square millimeter cable and a 40 amp breaker to protect it. But then you look at the lighting circuit, way less power, so it only needs a small 2.5 square millimeter cable and a 16 amp breaker. Everything is custom fit and protected for the load it's serving.
And here it is, the final blueprint. This is basically the instruction manual for the installation crew. It clearly lays out every single circuit coming off that main board, telling them exactly what size cable to pull and which breaker to install. No guesswork needed.
Okay, before we finish up, let's talk about a few things that separate a good design from a great one. These are the final checks that really make a system professional and rock solid. So for bigger projects, we're not quite done. We check the power factor. That's all about making sure we're using electricity efficiently. We'd also look for harmonics. That's basically electrical pollution from modern electronics that can mess with other equipment. And maybe most importantly, we follow strict codes like NEC 700 to make sure that life safety systems, fire alarms, emergency lighting, are on their own dedicated bulletproof circuits.
So I want to leave you with this one thought. We've talked a lot about codes and formulas and calculations, but beyond all the technical stuff, what is our single greatest responsibility? The formulas are just the tools. Our real job, our core responsibility, is to use those tools to create a system that is fundamentally safe for the people who will live and work in that